today. So, welcome. Welcome to Unlocking Innovation Programme, sponsored by and supported by our partners, Network Rail and the UK Rail Research and Innovation Network. Can I also draw your attention to something that we're doing today, which is on behalf of the Rail Technical Strategy team, we are collecting data from organisations on the call today that are working in the area of data-driven maintenance. So I'll shortly put that link into the chat. It's a very straightforward form, and it allows you to put your details forward, your company name, your organisation, and the kind of work that you're doing in the arena of data collection. And that basically, that's all about making sure that your company gets recognised in the rail technical strategy work as being a company working in that area. So this is a good way of publicising your work in data-driven maintenance. So today we're going to be talking about collecting your data later on this afternoon. Tomorrow we're going to be talking about interpreting data, and in the afternoon tomorrow we'll be talking about how they use that data to change your business. The link is the same for all of the sessions, and at the end of each session we'll have some informal networking. So this morning, and I'll talk you through this morning in a moment. This morning we're going to have an hour and 20 or so presentation, and then 30 minutes informal networking. So if that's what we're doing later on today and tomorrow, what is it we're doing today then? Well, we're focusing on knowing your asset. So before you start collecting data and interpreting data, installing sensors, etc., you really need to understand about your asset, how it works, how it deteriorates, how it fails, and what is it you should monitor and measure and collect data on. Should you measure everything or just the critical items? And we're going to explore those questions today with our speakers. So just before I go through the speakers, if I could just remind everybody, if you could turn your cameras off and microphone off until the networking. First up today we'll have Ian Bridges talking about the age of the intelligent railway. Then we'll follow through with data-driven deterioration modelling, looking at structures and bridges with Neves and Gareth Calvert. And then we'll go out of the rail industry and look at an adjacent industry, in this case nuclear submarines, with John Constable of TP Group, understanding how you assure 95% availability on critical systems. We'll then look at, we'll hear from Colin Johnson on how they're using asset data within their business at D-Gauge. And finally, we'll round out the morning with Colin Smith McGloin from Unipart on in-service monitoring. So that brings me to my first speaker. And if I can invite Ian Bridges to join us. Good morning, Ian.
Good morning.
Right, I will stop sharing my screen and invite you to share your screen whilst we do some introductions. So Ian is professional head of signalling at Balfour Beatty, but importantly and relevant to today, Ian is this year's president at the Institution of Railway Signal Engineers. And Ian is going to present on his presidential theme for this year, which is the age of the intelligent railway. And Ian will explore what that means for the railway of the future. Ian, can I hand over to you to give your presentation? Thank you.
Thank you, David. So, good morning to everybody. What am I going to talk about today? Well, first of all, I'm going to tell you a little about myself and then move on to some of the things about the IRSE that some may or may not know. Then a little bit about the intelligent railway and what I see as the intelligent railway, and then perhaps some benefits on data-driven maintenance, and then before just finishing off on just a little bit about the future of the institution of railway signal engineers. So, who am I? Well, I'm a career railwayman. I've got almost 44 years in signalling, telecoms and railway systems. Not quite, I've got a little bit to go until September, but we're nearly there. So my career was split into different parts, really. The first part of my professional life, I started as on telecoms, as a training technician on telecoms in Crewe back in 1977. But most of my early part was spent in signalling design and in testing. So then, post-privatisation, I moved into sort of more general engineering management, joining various companies such as Balfour Beatty, Signalling Solutions Limited, and Atkins throughout my career, and took part in a lot of engineering management and development of new products, principally interlockings. So then it all got a bit too much for me, so I retired in January 2019 on the Friday, and started again, as most railway people seem to do these days, on the Monday, probably what is my final chapter, in fairness, returning to Balfour Beatty after a break of a few years. So I've gone to Balfour Beatty to help start a new signalling business there because of various things that happened over the years with Signalling Solutions and Alstom and so on. Balfour Beatty didn't have much in the way of signalling support. So in 2019, I went back there to do something new that I hadn't done in the previous 42 years and help to build a new signalling unit. So the IRSE has been part of my life for a long, long time, really. It started when I joined as a student member in about 1980. A lot of people in the design office in Crewe, where I worked by then, were members of the IRSE, and they saw it as a great learning tool. So I was encouraged to join. So I did that, and in 1982, I joined the section committee of the Midland North Western section, and I actually still continue to do that today. I did have about a 1 year break in the middle when I did my MSc, but basically I've been doing that role since 1982, so it's quite a long time. So I've been part of many other committees as well. I still sit on the membership and registration committee within the sort of the headquarters part of the organisation, and of course I also sit on a number of other committees now as president of the institution. But I've sat on various committees and done various things over the years, so it's all been very interesting. I've attended lots and lots of talks over the years. I find that it's been really useful to help my progression through the industry, and I've also attended quite a lot of lectures outside of the industry as well, because I think as an engineer it's quite important that you get a broader feel for what engineering is all about, not just close to where you work. So later on, when I got a little bit more money in my pocket and so on, I managed to start attending the annual conventions and the aspect conferences, which they now alternate. They used to be both in the same year, but they now alternate. And that's got me to an awful lot of places around the world that I never thought I would get to on my own. We've been to Australia, we've been to Thailand, we've been to China, we've been to India. It's fantastic place I've had the opportunity to go. So I still attend quite a lot of continuous professional development events. I also present some myself now, which is a bit of a turnaround. So the IRSE has been really important to me through my career. So a little bit about IRSE governance. Not everybody wants to become president. Most people are happy just to be members of the institution and like I have, learn from the institution. But if you do want to become president, then you can do that by applying to join council. There's elections for council every year, and a part of the council rotates. So there's always an opportunity to come on to council. And at that point, you become a trustee of the charity. And you can have your voice on council. If there's something you don't agree with the way IRSE is run, then that's your opportunity to get onto council and voice that opinion and see if things can be changed. So having become the junior vice president, then you do 2 years as senior vice president. I beg your pardon, 2 years as junior vice president, 1 year as senior vice president, and then the year after that you become the president. So as president of the IRSC, you are effectively the chairman of council. So the council is the decision-making body. As I say, they're the people that ratify all the decisions that are made for the charity. So you become chairman of that council. Effectively, you're leading the business. So you also take on duties to help manage the business finances, and you become a director of IRSC Enterprises, and that is the sort of parallel organisation that is set up to run things like events and so on, that can help to make some money for the institution. So the management of the institution is governed by the council, as I say. Elected representatives now serve 3 years. We changed that in the constitution at the last AGM. It was previously 2 years. It's now 3 years. There was a lot of common sense in doing that, because when you're trying to manage the progression of presidents through the seniority, it gets difficult if they're re-elected after 2 years, because there's always that opportunity to vote somebody off the council who's in the presidential chain. So it was changed from the point of view of making things more secure and planning for the future. So sitting alongside the council is the management committee, where policy is discussed and where objectives for the institution are set. None of the decisions that come out of there can actually be implemented without going to council first. So normally there would be a management committee meeting, decisions would be made at that and agreed amongst the presidential team and 1 or 2 others that sit on that committee, and then they would go to council. As long as council agreed to that, then it can be put into the constitution, but it has to be council that accepts them. So sitting below those, there's committees that have delegated powers on various different things, such as licensing, membership and registration, managing the IRSC examination, and so on. There are others as well, such as audit committee and so on. So they're sort of like the powerhouse, if you like, of the institution. It's all run by volunteers at that level. There's the number of committees, each having a chair, who report back into council for various things. So as I said earlier, I sit on membership and registration. We meet roughly once a month throughout the year, review all the applications to join the IRSC, and we review all the changes in membership class that people have applied for as well. So and then underneath there again we have local sections, which there's a number of them in the UK, but also there's a number of local sections throughout the world, and they all manage their issues locally under the banner of the IRSC. So although there's strong links into the IRSC, and they do report into the IRSC through annual reports, and they're also funded by the central body in London, they actually work relatively autonomously. So the IRSC in the wider world, well, it is very much a global organisation now. You can see from the graph on the right-hand side there that about 52% of the membership are in the UK, and about 48% of the membership is non-UK. And that is gradually drifting towards being the other way around, where we'll actually have probably slightly over 50% of our membership abroad. And you can see in the graph at the bottom there that there's big chunks of membership in Australasia, in where's the next biggest one? The next biggest one in India. We have 249 members in India, and we have sort of around 150 or so in a lot of the other sections. Some very small sections. Thailand only has 24. Indonesia only has 34. And these are sections that have not been long formed, and are now growing. The constitution says that you have to have so many members in the local section to form it. Once you do that, the section can be formed and then becomes one of the autonomous sections with support from London. So gradually becoming more worldwide representative of the railway industry. So the IRSC continues to hold events around the world supporting its membership, and one of the important things it does is creating a body of knowledge. And it's been interesting really, because with the World Health situation over the last 15, 16 months or so, obviously everybody has been attending video or webinar type conferences rather than being there in person. And what this has forced us to do is to record those events so that people can watch them elsewhere. So not only are we finding that we're getting a lot more people attending these events, and in the case of the Middle and Northwestern section where I sit on the committee, we've sort of gone from an average of around about maybe 30 to 40 people attending a lecture, and that's quite a high number for some of them, to somewhere in the region of 150, 160 people attending. And not just from the Middle and Northwestern section, of course, but from generally UK because of the time slots, but from around the rest of the world as well, certainly from the rest of Europe. And once those are now recorded, that we have our own Vimeo channel now, so people can go onto the Vimeo channel and watch the videos later at their leisure. So this body of knowledge is growing quite considerably, and probably if we look at the in percentage terms over the last 15 months, it has grown phenomenally compared with previous collection of information. So because we had to move on because we were suddenly all in lockdown, we couldn't attend events. So what we've got to do now is put plans together for future events, enabling people to once again meet together. As David was saying at the start, one of the things we've got to learn how to do now is to have hybrid meetings where we can have people in attendance, but also people attending by webinar. And it sounds easy to do that, but there's actually quite a lot of issues around getting that sorted. So that's going to be our next forced area of learning in moving the institution forward. So moving on to the intelligent railway. So each year the president chooses a theme for his year, which is of interest to him or her, and that is sort of aimed at moving the industry forward. It might not be that they do anything as an individual to move it forward, but by collecting together seminars, lectures, and so on, visits, the president can help to influence that. So partly because of my previous roles in the industry and my current role, I decided to choose the intelligent railway for mine. It's interesting that people try to define what is the intelligent railway and also what is the digital railway. I hear the term digital railway probably several times a day, certainly several times a week. And yet in some ways the railway has been quite digital in signalling terms since about 1985 when SSI was invented and the first commissioning took place at Leamington Spa. That was digital technology. It's obviously it means something slightly different today, but it is only a progression from there effectively. When assets are failing or before they fail, so that we can avoid surprises, to stop things failing in traffic so that we delay customers, both passengers and freight. So it's eliminating that downtime, and it's all about collecting the relevant data to make sure that we can do that. So taking the raw data in suitable quantities, and I think that's an important word, suitable quantities, and then processing it to make it useful is what it's all about. I think there's an awful lot of people feel that data just has to be collected because it can be collected these days, and then that data is not used effectively or is never used at all. So it's not really very purposeful collecting it. So as I say, it's about suitable quantities and then processing that data. We need to identify what extra data we might need. We might be short of a little bit of data. We might have to go and collect some more data that we don't already to complete the picture. An example I gave recently was level crossing barriers, where if you get a level crossing barrier that's slow to lower, you might notice that it's slow to lower, but you might not know why. But if you then look at temperatures, you look at wind direction, you look at wind strength, you might see that it's the wind that's blowing in a certain direction is stopping that barrier falling. So it's about collecting those important bits of data and creating an overall picture to show you what is actually going on. So then it's feeding that data back again, feeding back to the right in the right format to the right people. If you take Network Rail as a client, then people in senior positions are not particularly interested in a particular component failure, but they are very much interested in whether their railway is in good shape. So maybe something not much more than a series of green traffic lights or green smiley faces or something like that is good. But when you get down to technician level, he needs to know before he goes out there what's failing, what components to take with him, what might need replacing, and then make provision for doing that. So by monitoring and assessing constantly, some normal operational parameters can soon be understood. Your barriers falling for sake of argument or your points moving, they will always move in pretty well the same amount of time. It will vary just a little bit, but you'll get a tolerance. Once you've understood that tolerance, you can then start to set alarms so that if the equipment falls outside of those parameters, then a potential fault is going to occur. It might be the points have started moving slowly, so there's some sort of problem with the points that may be just simply greasing, or it may be something a bit more serious. So then again, as I said before, the correct parts can be assembled, taken to site, and replacements made in due time. There's an example. You can see this was a bolt coming loose on a level crossing, and you can see that it happened sort of pretty well every year. So they do cyclic maintenance, but by the end of that maintenance period, the bolt was coming loose again and creating a problem with vibration on the barrier. And you can see on the right-hand picture there, the vibration caused as the barrier falls, and then an increasing amount of vibration as the barrier rises. You can also do that. You measure that with inclinometers fixed to the barrier, or measure by measuring motor current as well. So when alarms are generated, priorities can be given. They can be passed on to the maintenance teams, who can decide which of the ones that's got an alarm at the moment is the most important to go and fix. And eventually, you can actually probably eliminate some maintenance activities as well. This is one of the things that we're looking at the moment, is how you can get boots off the ground, thereby reducing carbon emissions by having to drive to sites at 4 times a year potentially, and also increasing efficiency. So cyclical maintenance becomes replaced by targeted maintenance, and therefore increasing efficiency a lot more. So what's the future hold for the IRSE? Well, it will continue to build its body of knowledge. This is something that's hugely important. As I said earlier, it enables people to find out information in their careers and use that for their roles or for learning. Modernisation of the institution will continue. We started this process probably about 18 months ago, a governance review working group. And this is largely around embracing our worldwide membership. It's not about changing everything for the sake of changing it, but we have to do things in different ways because we now have an audience very much around the world. The International Technical Committee will continue to develop papers. They look at some of the sort of bigger issues of the day. They meet a few times a year, and that's signal engineers from all around the world, and discuss a very wide range of topics and put papers together to discuss those with the industry. So I have the mantle until April 22, when Andy Knight from Signet Solution takes over, and he'll become president for the next 12 months. And his theme is going to be engage the people, deliver the goal. So that's looking at the people side of the industry as much as the technical side of it. And then for the year after that, Steve Bosher in 23-24 takes over, and he's based in Australia. So this is embracing the worldwide role of the institution, and he will be the 99th president. So thank you for listening. I hope you've learned a little bit about the institution, a little bit about me, a little bit about what I've done. Does anybody have any questions?
Thank you very much, Ian. Thank you for the overview of IRSE and also your focus on the intelligent railway. While we're seeing if other questions come through, if I could ask you a question, Ian. Where would you obviously, given your signalling background, you focused on data collection, analysis, etc., RCM within signalling. From your knowledge of other sectors, where do you think signalling is in the sort of in its journey compared to other sectors?
Yeah, it's an interesting question. Though I think it's very patchy. I mean, certainly on a worldwide basis, it's extremely patchy because some railway organisations have not gone very far down that road at all. But if you take the UK, I think it's still a little bit patchy here because we have some very modern pieces of railway in the UK, but we also have some bits of railway that are maybe a little bit older, should we say, being polite. So I think compared with other industries, we take like the aircraft industry, for instance, as a parallel, I would say that they're probably in front of the railway industry because monitoring of aero engines, monitoring of systems on planes, monitoring of airports and everything to do with aeroplanes is probably well in front of us. But the rail sector is catching up. It now knows how to collect data. It now knows how to process data. And if we can find ways, as I was saying, about collecting it from some of those perhaps more obscure areas to help us there, then maybe we'll be catching up pretty soon.
Thank you, Ian. You touched on there the important bit about collecting data and turning it into information and then effectively action. So how you talked about dashboards versus granular detail for technicians. Would you like to say a little bit more about how you avoid or how you choose the right data to monitor and how you choose the right data to present to different audiences?
Mm-hmm. Well, firstly, I think it's understanding what the client wants. I mean, different clients want different things, understandably. So I think that it's very much about engaging with the client at the start of this process to understand what it is that they want. Now, I said that I felt that somebody senior in a business, particularly like Network Rail, might only want traffic light system or something like that. But it may be that isn't necessarily the case, and that they do want more detail of what's going on. So it is possible to provide that, but what you've got to do, I think, is make sure that you're providing the right information to the right people through conversations, through scoping out what you're trying to do. Because if you send all of that data to senior people, it's just too much, and it becomes bewildering, and they haven't got time to sit down and work through it. So a simple traffic light system might be appropriate. But at the other end, the technician can dive into the system to have a look more at what is going wrong. He can look at replays. He can take data offline and replay it and look to see whether the same thing is happening each time, or whether things are getting worse, or whether indeed it was a momentary glitch that was reported. So it's very much, I think, about talking to the customer, understanding what the customer wants, and then providing that amount of data to him, which can be changed later on. But if you try to get it right in the first instance, that'll be good.
Sounds great advice, Ian. So if I could thank you very much, Ian, for your opening of applause from 90 people. Thank you very much for your opening presentation. There goes the rounds of applause. Excellent. That's fantastic. If you'd like to unshare your screen, and I invite our next speakers up. Dr. Lewis Neves and Dr. Gareth Calvert from the University of Nottingham and Network Rail, respectively. Do you want to put your cameras on, Lewis and Gareth? Good morning.
Hi, good morning.
Welcome to the Unlocking Innovation data-driven event. Lewis has worked on the development of asset management models for transportation infrastructure for over 20 years. He's developed and applied, in conjunction with industrial partners, innovative frameworks for decision-making and bridge asset management. Gareth has developed novel stochastic deterioration modes for existing bridges, accounting for interactions between deterioration models. And he's currently working in Network Rail, applying these models to real structures. So we're now going to take a real look at the challenge of modelling deterioration with a practical study from Lewis and Gareth. If I can hand over to you, gentlemen. Thank you very much.
Thank you. I hope you can hear me and that you can see my screen. Great.
Perfectly.
So my name is Neves. I come from the University of Nottingham. I'll be making this presentation in conjunction with my colleague and good friend, Gareth Calvert. And we're going to be talking about the work we've been doing with Network Rail on data-driven deterioration modeling. So the main motivation for this is that, as we all know, Network Rail is responsible for maintaining a huge network that involves around 26,000 bridges. And Network Rail applies lifecycle models across the entire portfolio to predict the future asset condition, but also to calculate residual value, evaluate different management strategies, and justify decisions to stakeholders. So when they are requesting funding for different actions, they need to explain how that is going to work out in the long term. Now, to do this, typically we use what we call bridge management systems. There's quite a few of them around. Some Cuba, Pontish, Dambro, Bridget from US, from Switzerland, from Denmark. The problem is that most of them are based on very simple Markov chain modeling, which is a way of predicting future deterioration, which is quite limited. And so as a result, the main benefits of these management systems are fundamentally a database or an inventory of the structures and the prediction of the next maintenance action. So they actually do not allow comparison of different strategies. They don't allow to estimate long-term costs. They go as far as the next maintenance action. And so what we're going to look today is what is the strategy that a Network Rail uses and how we can contribute to make that strategy more efficient. So Network Rail works in a set of tiers that Gareth understands much better than I do and that he will explain.
Perfect. Yes. So at Network Rail, we have a plethora of decision support tools and models that exist, ranging from ones to support operational decisions in real time, all the way up to strategic priorities in the long term. So in terms of whole lifecycle modeling, we have 3 tiers of modeling. I'm going to begin with tier 2, which is a strategic level model, which is used to assess the long-term outlook on generic systems or generic assets, and it's used to determine asset policy that will yield the optimal whole lifecycle cost. Once we've determined the asset policy that returns the optimal whole life cycle cost, we feed that into a tier 1 model, which is again a strategic model, and that is used to forecast costs and volumes in the medium term, and it's primarily used at Network Rail for multi-control period planning. The third tier of whole life cycle modeling is a more tactical level, and that is at local level for specific systems or specific assets, and is used to ascertain the best renewal option for a specific project. In terms of the work we're going to talk about today, it's more at the strategic level, so tiers 1 and 2. So I'll hand back to Luis at this point.
So what we want to do is to develop a methodology to model the deterioration of breach at network level. And we want to do this so that we can maximize the impacts of investments and minimize the safety risks to the infrastructure users. And so we want to develop lifecycle models that address all phases of the life of the bridge, so deterioration, inspection, decision-making, and maintenance. And then we want to evaluate the impact of local conditions on life cycle decisions and costs. Then once we've done that, we want to look into situations where you have multiple defects interacting with each other on a single component, and then identify and quantify the interactions between this. And so by doing this, develop a lifecycle model technique that allows us to address specific defects. So how do we go about getting data for this? And then how do we go about using this data to produce models? So the fundamental principle is that a bridge in Network Rail is divided in components, and a bridge can have dozens of different components, and each of them is inspected at regular intervals, and that inspection results in a score. Typically, the score that Network Rail uses is a alphanumeric scale where the number refers to the extent of damage and the letter refers to the severity. So A means perfect, and then B, C, D, E, F, and G, increasing severity of deterioration, and 1 to 6, increasing extent. There's actually an additional scale called CM for coating and paintwork, and that is relevant for the work we've done later on. Now, the way this has been used is that this score, which is very intuitive and quite physical, is converted into a one-dimensional scale where this is 0, 2, 3, 4, 5, 6, 7, 8. And this conversion has some advantage because it allows the use of Markov chains to model deterioration, but it's not particularly intuitive, and it doesn't really make much sense, for example, to move from a 9 to a 10, because that would mean that the extent of damage would be reduced, which is not something that we usually see in reality. So the data we have to develop our models based on this framework comes from 2000. So we have 20 years of data for a very large number of bridges. And so we are able to actually get some nice information out of that. So the approach we've taken is to use something called Petri nets. Petri nets is a model which is ridiculously simple. It was invented by a 12-year-old child. Okay, the child became professor of mathematics at some point, so he was a very bright child, but he was a child. And the principle is that we have places, and places indicate states of the system. And then tokens indicate where the system is, at what state the system is. And then when something happens, we have transitions. And when a transition fires, the state changes. And these tokens here move to the next stage. So this is a very simple model where things are in one place, tokens, they move to another place to reflect the change in state. And the original Petri nets are assigned a zero transition time. So when all the inputs are filled in, the transition is activated and something is output. This is not particularly useful. So what we can build on that is stochastic Petri nets, where the time for the transition to occur is a random variable. So this starts allowing us to do things like, okay, if this is a less deteriorated and this is a more deteriorated, there's a distribution for the time to go from here to here. Or if this is before inspection and this is inspection, there's a time interval that goes between inspections. And so this allows us to model a few of the phenomena that are relevant for bridges. And then we can move on to color stochastic Petri nets, which allow us to model different assets. So 4 different beams, for example, 4 different girders in the same model, and they can be in different places of the network depending on the deterioration. Some of them might deteriorate faster because they are on the seaside. Some of them deteriorate slower because they are protected from the wind. Now, doing that, we start developing models that combine deterioration at a sub-element, so a part of a girder. Then that results in a decision-making that says, okay, if we have this information at parts of the girder, what is the condition of the girder? Now, in bridge management, unlike signaling, there's very limited monitoring. So we only actually get any information from the bridge when an inspection is carried out. An inspection is a difficult process. And so when we have an inspection, we have a revelation of the condition of the bridge, potentially with errors. And once we have that, we can make a decision based on the condition of the bridge. And that decision will potentially involve some intervention, and the intervention will change the condition of the bridge, and then we go back into the deterioration model. So this is how we model the overall component of a bridge. So what have we done with this? We started by modeling a bunch of reinforced concrete bridges, and then the models seemed to be relatively accurate. And then we went into a situation where we wanted to analyze what were the factors influencing deterioration. So where should Network Rail put the money regarding inspections, regarding maintenance, regarding monitoring, if that was relevant. And so we looked at, if you were talking about underline or overline bridges, the traffic loading, the speed, the galvanic response is a particularly interesting one. I'll get back to that in a second. And the distance to the sea, because we all know that sea tends to induce corrosion. And the galvanic response is quite an interesting one. So the Galvanizers Association leaves some coupons of steel spread around the country. And from time to time, They go and they inspect these coupons, they measure the corrosion levels, and then they classify every location in the country in a rank of 1 to 5. Now, it's reasonable to consider that the corrosion of these coupons is correlated with the corrosion of steel in metallic bridges or reinforced concrete bridges. So we analyzed all of this, and what we saw is that underlying overlying bridges were different. Our loads really make no significant difference, but galvanic response and distance to the sea make a huge difference in the deterioration profile of bridges. So if we look at the results we have, if we start here with an overbridge, very far away from the sea and at a low corrosion level, and if we start with a new bridge here, the dark blue represents the probability of the bridge being in pristine condition. And what we see is that a lot of bridges deteriorate, but after around 12 years, we still have a probability of around 65% of the bridge being in absolute pristine condition, and a very small probability being higher deterioration levels. If I keep moving to higher corrosion levels, or if I go to the worst conditions, which will be very close to the sea and at a high level of corrosion, so probably in close to the sea in an area with heavy industry. At the end of the same time interval, 12 years, instead of having a probability of not being pristine of around 65, I'm down to 15%. So this bridge will be tremendously more expensive than this one. And not only that, the risks associated with having to repair it as an emergency are much higher to the bridge on the right than the bridge on the left. So if I'm going to spend money on monitoring and inspection, I should put it here rather than here. And this is how we've changed the policies in our work well regarding the planning of inspections. Now, once we started looking into metallic bridges, we realized this actually was not a very appropriate way of solving the problem for metallic bridges. Gareth?
Yep, no, I'll pick it up from here. So yeah, just to recap, existing practice at Network Rail was to use a single indicator. At a Network Rail, it's a rather arbitrary indicator going from basically good to bad. The work Luis just described moved over to the SEVEX scale and was describing the worst SEVEX score at any given time. However, for metal and the severity extent scale, how it's defined, there are clearly identifiable mechanisms, namely the condition of paintwork, the rate of corrosion, and the development of structural component failure. So initially, we tried to do some preliminary analysis on trying to get 3 simultaneous indicators for each of the mechanisms from SEVEX. And we did that using Markov chains, and the initial analysis got us some interesting condition profiles and reasonable prediction accuracy. However, the approach with Markov chains required a massive assumption, and that assumption was that there was an independence between these different defect mechanisms. So more recent work, we've looked at trying to incorporate the interactions between the mechanisms. And we did that using a Bayesian belief network where we had the condition of paintwork influencing the rate of corrosion and the rate of corrosion then influencing the development of structural component failure modes. And I said Bayesian belief network, but for those that are interested, it was actually a dynamic Bayesian network to evolve it over time. So in terms of these deterioration models, some of the outputs we would get are condition probability profiles. And a condition probability profile is basically, next slide, sorry, Luis. A condition probability profile is basically the probability of being in a particular condition states over time. And I don't want to go into too much detail, but the dashed lines are from the independent Markov model and the solid lines are from the dynamic Bayesian network, but one includes the interactions. And what we observe from these deterioration profiles is that if the mechanisms are modeled independently, actually what we're seeing is there's an overestimation of deterioration early in life and an underestimation of deterioration later in life. And that's a particular problem given the maturity of the asset portfolio at Network Rail. Additionally, the incorporation of this non-constant deterioration behavior is massively important when it comes to modeling or evaluating asset management strategy, particularly around preventative maintenance, which is what we moved on to look at again using Petri nets. So the Petri net model shown here is quite similar to the one that Luis described earlier, except it's been altered to include transitions to allow for the parameterization of this multiple defects and the interactions between the multiple defects. And once we had this model developed, we then looked at incorporating preventative maintenance strategies regarding paintwork renewal, going from paintwork renewal every 5 years to not doing it all, and then assessing or evaluating the impact that would have. So again, we then yielded some condition probability profiles, or I think that in this case, it's average conditions. So the one on the left for paintwork, and not surprisingly, the earlier you renew the paintwork, the better the average condition of paintwork. But what we were then able to quantify was the benefit that this better paintwork would have on things like corrosion and structural component failure. Additionally, one of the benefits that the PetriNet model brings is that you can quantify metrics that are quite meaningful to the asset manager. So there's a lot of metrics to do with cost and poor condition that we can get out of the PetriNet model. It's quite beneficial to our modeling. So then finally, we then went about reconfirming with statistical significance a lot of the factors that Louise mentioned earlier about altering the life cycle profiles of things like coastal proximity, material type, annualized loading. And once we reconfirmed that these still remain valid for the multiple defect model, we were then evaluating them using a PetriNet model that determined that particular cohorts can have a significant consequence on the requirements to deliver particular management strategies. Asset management activities may be coordinated strategically at network level. However, it is common these activities are operationally managed in smaller administrative regions. And the inclusion of the deterioration properties enables a more equitable allocation or guidance of resources between the regions and routes at Network Rail to better accommodate the local asset management concerns. So depending on the selected asset management strategy, the model that incorporated the additional properties forecasted up to 40% more required resources than what the baseline models would have initially suggested. So the inclusion of these properties is hugely important when seeking to provide accurate guidance to our stakeholders.
So, quick conclusions, I would hope. We've been working with Network Rail on developing probabilistic frameworks to model all aspects of the life cycle of bridges. And I think this is quite different from traditional asset management systems. We're also working on including things like local environmental conditions. We know that bridges in different conditions deteriorate in different rates, and we need to be able to include that. And we also starting to learn about interactions between different deterioration mechanisms. And it's quite relevant to us because that allows us to not only develop maintenance strategies that can predict the consequences or can be defined taking into account the future consequences as the current condition state. So if paint is not working well, in 10 years' time, that is going to cost something else, which is a lot more expensive. If I can model that accurately, I can make decisions regarding paint that I can justify as spending money now is going to save me a lot of money later on. The other problem we are trying to get on with is this notion that a bridge is built of multiple elements and all of them are at the same location. So all of them are going to be strongly correlated. This is quite a tricky problem because we don't necessarily have enough data to do this. And then we are trying to work on methodologies to facilitate enhanced network level decision making. And this raises one of the problems we have with PetriNet, is that they are computationally expensive models. And so scaling them up is a bit of a challenge that we are working on. And I think I'm done. If there are any questions, please go ahead and we'll try to answer them the best we can. Thank you.
Thank you very much, Louise and Gareth. We really don't have very much time for questions just now. But you are going to stay behind for the networking, aren't you? So that'll give us a chance to pick up questions then. There's one question from the audience, which we'll just very quickly ask if we may, as it's come up. So you were talking obviously about deterioration modeling and long-term decision making. So the question is, how do you use data to make decision making on a daily and hourly basis? So, you know, if you're looking at the more strategic, in your 3 circles, you didn't talk about the tactical. So you want to talk a bit about the tactical for a second or so?
Yeah, I might. Well, I believe there's a bit of a problem here, which is our first guest talked about monitoring structures. And the problem with that is that the amount of bridges we have and the fact that they are so different, this requires a design process for the monitoring itself and the amount of data we get is just ridiculously high. So what this work we've been doing, what this does is identifies higher risk structures. And by doing that, he identifies the structures that need to be inspected more frequently, but also the structures that should be monitored, because the value of the information you get from the monitoring compensates the cost of installing the monitoring. And that's what's going to drive decisions which are more tactical based on daily or weekly or monthly decisions. So what we're trying to do is not guide decisions on individual bridges in terms of maintenance and repair, but identify on which bridges should you invest money on gathering more data and making more careful decisions. Does that make sense?
It does. Excuse me, I'm just trying to get our lights to come back on again.
I was wondering what that meant.
Thank you very much for that, Luis and Gareth. If we could ask the audience to indicate their thanks with the sort of clapping icon, that would be great. So thank you very much, everybody. So Luis and Gareth, if you could come back for the Q&A later, that would be brilliant. If I could invite now our next speaker, which is John Constable from TP Group. John, do you want to join us? Hi.
David, hello. Can you hear me okay?
Yes, I can hear you perfectly. Thanks, John. So welcome. Are you ready to share your slides?
I am, yeah.
So I'll just introduce you. So John is the Managing Director, Atmosphere and Clean Energy Systems at TP Group PLC, who's going to talk to us about critical life support systems on submarines. You might wonder why that's relevant to rail. Well, we always like in Unlocking Innovation to bring in an expert from an industry or technology that's external to rail to try and encourage cross-pollination and learning. And of course, TP Group are, well, as it says on John's slide, looking to bring some of the thinking from the defence work into rail. So without any further ado, John, if I can hand over to you, and I look forward to hearing your presentation. Thank you very much.
Thank you, David, and thank you everyone for listening to me today. It's really good to be here to present. Hopefully everybody can see my slides. My slides showing, David?
Yes.
Yes, they are. Yeah.
Yeah, just dropped off the screen. So, yeah. So I'm John Constable. I'm the MD of our Atmosphere Systems business. I'm part of TP Group. So TP Group is a PLC, and we're a business that brings together a range of smaller businesses that have technology consulting experiences across many sectors. Primarily, we work in the defence, energy, rail, and space sectors, bring in a number of our technologies, including artificial intelligence, machine learning, hydrogen work, and also atmosphere systems in submarines. We're a global provider of atmosphere systems to submarines from UK all the way through to Australia. So we've got a lot of experience in deploying those systems, and we've been around since 1957 as our business as it is. So as you can see, there's a lot of experience. So we tend to provide end-to-end systems for our customers that provide clean atmosphere. The clue's in the name, really. And we're currently working on a range of intelligent hydrogen refueling stations for the rail sector. And we're also delivering some hydrogen fuel cells into the Hydroflex project. So just to put a little bit about our rail credentials. So submarines and trains, I guess questions in the audience may be, well, what's the similarity between submarines and trains? Well, there's quite a lot in terms of how the submarine endeavour works and how that probably compares to the train sector as well. We found a lot of connectivity in between the two ways the markets work over the last 2 years we've been engaged in the sector. At a system level, it's a very similar concept. They're both very highly regulated industries. There's a lot of safety and regulation that goes in there. It's government-backed industries generally, which means that it's all about making sure that the end customers are safe in what they need to do. There's a long life expectation. So everything that we work on in our defence sector has at least a 30 to 40 year life expectation, which is probably very similar to many of the subsystems and systems in the train network, in that, a train has a 30-year life expectancy as well. Safety first. So in the submarine market, You know, you're hundreds of meters below the sea. It's a pretty hospitable environment, if I can say it. And because of that, it means that you have to be very safe in everything you do. It's a sealed tube. You're doing all kinds of things like generating dangerous gases within those tubes. You need to be able to manage that carefully. And principally, people need to be able to breathe. In the train sector, it's all about making sure that obviously trains get from A to B in a safe manner and arrive on time. There's a lot of advancements happening in the defence sector. Many of the things that we see, we think are applicable into the train market as well. So there's a lot of parallels there in terms of the two sectors and how they work. So from a submarine perspective, it's a 30-year lifespan, but obviously they have refits every so many years. So there might be 3 or 4 refits in life. That means that the platform goes into a long dock period, and a number of the subsystems are reconditioned, refurbished, replaced, upgraded to keep them going, which we'd imagine is very similar to a lot of what happens in the train sector as well, because it's clear that, you know, complex equipment on these systems probably won't last continuously for 30 years, 40 years, 50 years without interim servicing, which is kind of what brings us on to the topic of asset management and intelligence around asset management, which I'll come on to in a minute. Most of the platforms have a mix of technologies on them and equipment. The equipment and the services will be brand new, some of it, and some of it will be aging. Some of it's been there a long time. And the real challenge in the environment, both in the train sector and the defence sector, is managing how you keep those pieces of equipment working, how you keep the platforms working, how do you get from A to B safely, knowing you've got various failure points within your subsystems. And, you know, that's something that we all experience all the time in terms of systems and performance. So submarine system. So the picture on the right gives a kind of a high level perspective of our world, of what we do in the submarine market. So we provide an integrated atmosphere system. It's complex equipment. It's a series of interconnected subsystems. Principally, we take in seawater and power. And from seawater and power, we generate oxygen and hydrogen byproducts. We remove the CO2 from the atmosphere, which is exhaled by the sailors. And then we also have other treatment systems in there, which remove things like carbon monoxide, which is generated during cooking, as well as hydrogen, which often comes from batteries and other activities in the sealed vessel. So each of those is a complex component in its own right. So the oxygen generator is an electrolyzer. There's lots of talk about electrolyzers in the current market with hydrogen generation. Our systems principally in submarines generate oxygen. The hydrogen we have to remove, and we have to remove it in a sensible and invisible manner, because in a defence market, our platforms are not supposed to be seen or known where they are. Because those pieces of equipment are complex, there's a lot of technological challenges in there, specifically around keeping each one working for a long period of time. So there are many pumps and compressors, pipework, sensors, valves, controls, all those kind of things that, you know, obviously they have a lifespan on them. The systems we provide have to have a greater than 95% availability in terms of uptime.
Exit onto A4120.
So we have to manage that availability with the subsystems by understanding very much, you know, what's going on with the subsystem, both from an early requirements and design process point of view through to in-service operation and usage. So for us, it's understanding and designing out failure from the first point of call, if you like, from the early requirement phase all the way through to feeding back everything that we learn during operational service. Most of the systems have a window of 2, 3, 4 hours of repair on board. So there's a service level agreement almost in terms of being able to produce and do those repairs on board. So again, that kind of signposts the fact that the reliability is there, and that inherently there's only certain things that you can replace in that time span. Everything else has to be either dual redundancy, ultra reliable, or the ability to carry that spare part. The environment that these platforms work in is very harsh and remote. That's probably not too dissimilar to some of the work I've seen in the rail sector as well. You know, some of the conditions under carriage are pretty harsh as well. They may not be quite as remote. There certainly is a lot of harshness there. And our systems are designed very much to cope with harsh things such as seawater. Seawater ingress is very caustic and very aggressive. We have to be very careful how we manage it. We have to sense and control the systems to make sure things like seawater don't end up in the wrong places. Our systems have over 20,000 parts and components within them. So when you're managing that level of components in complex systems, it's absolutely vital to understand the condition, the health of those parts, and be able to maintain those, and then also be able to predict their performance over life. We have to manage invisibility. So again, predictability and understanding the condition of components is important. So just a good example could be reciprocating compressors and pumps. Each of those will have a noise signature associated with it, and we don't want any noise. If the bearings on the pump starts to fail, that generates more vibration, that generates more noise. All of these kind of things are critical for us to be able to understand and manage that out in process as quick as possible. So whilst that's unique to that submarine environment, the concept of doing that in everyday railway and transport applications is obviously very critical. Whilst the noise may not be such tight limits, the reality is the noise is a signature of a failure, and it's about understanding that to be able to manage it. And obviously the last point on the slide is around cybersecurity. In the rail world, absolutely you can get continuous data feeds. In our submarine sector, we don't have continuous data feeds because of the security around it, but we have internal feeds. So we have to be very careful how we manage data, and also the ability for systems to be attacked by other parties. And I think those are challenges also that are going to face into the broader transport systems network as well, certainly as we move towards autonomous vehicles. So data in a submarine refit example. So I thought I'd just talk through a typical case study for us in terms of what we do with the refit. So we have a series of sensors on the equipment. We have embedded control and data loggers, and have for many years. The data is tracked on all of the systems at regular intervals. We sample at quite a different frequency of rates depending what we're looking for, what we're listening for on the system, and we process all that data so it enables us to understand what's going on. Now, in our world, we can't transmit, but we can collect the data at key points in the journey of the submarine. So then what we're able to do is to use that data around the system performance. So how much oxygen are we generating? How much CO2 are we removing? How much noise signature is happening? Have we got any failures of components that have been logged? And it's really kind of picking up all that operational data and informing a view on exactly what we're going to do with that. We've been managing through life contracts on this for at least 30 to 40 years, which means that in days gone by, a lot of the collection and analysis of data was done manually. And obviously, as we move forward now, things are much more driven by data science and data technologies. So the data we collect enables us to make decisions around the condition, the health of the equipment that we've got on the submarine. So for instance, an oxygen generation system, we understand each of the points of the equipment through its expected performance curve, how it's performing, what's going on with it. And that enables us to make decisions around which components may need to be replaced at certain times in its life. We also have an embedded historical body of data from having operated for a long time. So you combine the two sets of data, both historical longhand data and current collecting data, and you're able to draw that picture of what we need to do. So what this does then is it enables us to solve the challenges of system reliability. If we understand which components are likely to fail in what time window, we can then plot where the likely refit point is going to be for that platform, and we can understand which bits we need at what time. The benefits for that are clearly around a supply chain angle, because if we now understand what components we want to replace when, and we know when the window of replacing them is, it means we're able to source and secure or design upgrades if necessary to replace components and subsystems so that they're ready for when the refit work happens. So what that does for us is that produces a reduced cost. So instead of us being on a short lead time, rapid delivery of components and having to pay extra for getting the parts where we need them, we're able to place longer term orders with our supply chain. We give a better visibility, and it also enables us to plan when the labour is available to go and support the system. So for us, that helps our business, but from the end user perspective, it means that they know that this is the works are going to be performed when necessary. So it is a preventative plan based on predictions of what we've got in terms of data. mean time before failure is a key part of the system design. So when we take on the design of the systems, we look at all the component mean time before failures, we make a judgment across a system level mean time before failure, which then means we're able to add in redundancies. So the data we take from operational service enables us to understand what is actually happening in the application when it's being used. We're able to feed that data back into the design considerations we had at the front end of our project, which means we can then inform the next system design that we do. Over the last 20 years, we've performed a lot of modelling and mapping to predict the overall health of systems across all of our customers. That enables us to provide that kind of level of service that we think is much more valuable than just reacting to failures as they happen. Whilst there are windows for repair on submarines and in refits, actually the reality is we probably want to be ahead of the game and make sure things are being replaced ahead of time. The outcomes for us are critical in this market, and I think if you look at using data within the refit application, that also is very applicable to the rail market. So we have to manage the operational uptime. It's all about making sure that the platform is ready to operate whenever it's needed at a moment's notice. And the only way you can achieve that is by predicting what condition things are going to be in, and by using the data to inform maintenance planning. As we move forward, it enables us to look at much more of a rolling schedule of works rather than specific kind of refit periods. So traditionally, large platforms like submarines and ships come in every so many years, and there's a complete strip down and refit. It's an extremely expensive process, and obviously it means that the platform is out of service for a period of time. If we're able to use data to predict the performance and enhance the performance of the subsystems, we're then able to reduce the time needed in dock, which then means operational uptime is there, which for a total operating perspective obviously reduces the cost, because the cost of having these platforms in layup for a number of years, between 2 and 5 years, however long it takes to do the rework, is an incredible cost to the operator. The life of the system is critical, and everything that we've learned over the last few years in terms of data collection, so failures that have been accounted for in the past, root cause analysis of failures, data collection today, understanding the system parameters and the operating window and feeding all that back in is something that's quite critical to taking this forward. Are we out of time, David?
Almost. Yeah.
Brilliant. So I have one more slide. Is that still on the screen?
You're on data within submarine refit at the moment.
Okay, it's just flicked off when you've come on. So if I just go to the future, we get the right one. That would be useful. Can you? Is that showing, David?
No, not yet.
Hold on. Sorry.
Don't worry.
That's all right. You'd think I'd be used to this by now, wouldn't you?
Aha.
Yes. Is that showing?
Yes, that's fine. Yeah.
Brilliant. So the future of certainly the maritime market is moving more towards AI and machine learning for advanced decision support. So actually what we're looking to do is to use those technologies to help us make the decisions, rather than at the moment, obviously, decisions are made based on analysing reams of data. AI technologies are great because actually then what we can look at is miniaturizing the systems. We can look at things like making them more autonomous. And then actually what that will do in the future is enable us to have much better logistical control. Now, the submarine market is quite unique compared to other sectors, but what we're seeing is that the trends there are following other sectors, and it is absolutely applicable to say that the things we've learned over in the defence sector in terms of high reliability, safety, data management, real world data management feeds into where the future is going to be and how we evolve all the subsystems and systems that we need to operate various things. And I guess probably a lasting thought would be, wouldn't it be great to look at mixed fueled fleets and how you manage mixed fueled fleets using AI decision support? So think number of trains running across the country, different terminals, different stations, different requirements, different systems, all the data, all the complexities of that, using AI to manage that, to understand, have we got on time, have we got the right carbon signature, have we got the right health on the assets. And that's kind of where I see the future going. And that's kind of the feed-in from the defence world. So thank you very much.
Thank you, John. We're going to have to hold questions, I think, until the networking session, which is in 20 minutes, if that's okay with you. So I've got a load of questions, really fascinating insight into another sector. So Colin's come straight on board, which is great. So can I ask the audience to thank John for his presentation with the applause or hands up or whatever, thumbs up symbol. So thank you, John. We'll see you in 20 minutes for the networking session. I'm going to go straight in and introduce Colin Johnson from D-Gauge. So we've got a couple of short presentations coming up from two Collins. Colin Johnson of D-Gauge is going to show us how his company are using asset data to revolutionise the gauging analysis in UK rail. So Colin, straight over to you, please.
Thank you, David. And let me share my screen. Thank you for everyone for joining us or joining me going through this kind of very short whistle-stop tour of data-driven gauging. A little bit about me in, I suppose, the theme which has preceded me. I'm a mechanical engineer. I started off my life in motorsport, which I suppose even when I was involved was incredibly data driven and very kind of instantaneous data driven to make decisions. So really powerful there. But I have been in the railway engaging for a decade, which I suppose does make me still very green behind the ears. A little bit about D-Gauge. We're a hybrid engineering and software company. We're a team of around 20. Our software is focused on delivery of high quality gauging information, and our engineering team really do deliver the most complex gauging projects around, normally when they span various disciplines, including freight, pantographs, and all sorts of new ideas. As a company, we don't collect data really. We tend to work with some really fantastic partners to do that. What we really do is focus on collating and processing data to correlate and add value to gauging, really. So that's what we're about. But for me, data is fuel. You'll forgive the automotive analogy. It doesn't necessarily relate to power, and like all of those things, we can use it crudely or we can use it smartly. I think we only have to look at engine performance in the automotive sector to see how economies and all those things come from fuel. The same with data. We just have to use it smartly. Key gauging data really for us, these are common themes to those in the industry. We need to know the vehicle. We need to know the shape of the thing that we're trying to fit. We need to know the infrastructure, which is the survey and where we're trying to fit it, and the rules by which we have to abide. The combination of those, how does it behave in atmospheric conditions? What about tracks? What about tolerances? Now, most of the industry know and love, I use that tentatively, these concepts, but there are other critical gauging data forms which really we can use to enhance our understanding. Permitted and timetabled routes. There are thousands of different operations, and particularly in the last kind of 24 months, we have looked at an unparalleled kind of change in our timetable systems. But it takes what goes where, and that's a complicated beast to understand. Future network changes, not just from power sources and electrification, but also upgrades of new fleets and the removal of other fleets. And our standards are changing at a furious rate to keep up with the technology which we're developing. Caveat really is I like this word volatile. Data can be that. A quote from the Oxford English Dictionary is liable to change rapidly and unpredictably. I think anyone who's had involvement in gauging has maybe fallen foul of some of these. Data can be volatile, and I think the point is snapshots of data can be exceedingly volatile. So that's gauging has particularly, to calculate clearance, the pursuit of gauging has been to collect data, and notoriously we've had to go through this process, or individuals involved in gauging, to understand what vehicles run there, what models should I use, how old is the gauging database? Has anyone got any survey information? All these questions are typically challenges involved in the gauging data. And I think that anyone who's had recent involvement in gauging over the last kind of 5 years could empathise with the challenge that some of these are and the time it takes. Where DGauge are trying to work with the industry is to move from gauging data to gauging information, to allow maintenance and designers to have that informed approach. And we it's looking about how things have got better or worse. Particularly if clearances are getting better. Why? We need to present that as information, not the data which gets us to that point. We're looking at trends. We're looking at how and when we maintain because of said trends. And I think a point which is not overlooked, but often difficult to appreciate is my data good enough? In the world where we have so much data, we kind of have to be discerning, I think. How does that relate to the gauging system? So look, I've put together a very crude ecosystem from where DGauges see the gauging implications. We have to plan and look at feasibility. So that's about evaluating change on the network, evaluating when we get new surveys and new infrastructure and new rolling stock, and that in turn, from that work, we trigger change. So that could be maintenance change, it could be upgrades. If you look at maybe a Transpennine kind of project, that would be looking at upgrading. If we're looking at the West Coast Main Line, that might be looking at triggering maintenance, critical maintenance. We have to commission network change and deliver network change. Those are outside the remit of gauging, but where gauging is really critical is about how we design and refine those. After we have made the commitments to change the network, how do we do it the most efficiently? So we are here to talk about unlocking innovation, and I think that we have worked really closely with Network Rail about how we can provide this better planning and feasibility. So we developed a new platform called DGauge Rift, and that allows Network Rail to automatically monitor change. We're looking at data, vehicles, and fundamentally monitor risk. So you have to forgive while I just lose the screen, and I'm going to actually jump straight into it for the purposes of this presentation. So so I hope we can see that there's we're now on a web browser. What we have as a network is we can monitor the network-wide clearance. Now, this is a compilation, as you can see, high level. We're talking about several 100,000 assets. We're talking about several hundred vehicles, and we're looking about monitoring the network. So this is monitored in live for the person Network Rail. Now, these are metrics which Network Rail are monitoring. So forgive the colours, it doesn't necessarily mean it's bad. All it does is it highlights where Network Rail want to focus their effort. It's a point where Ian Bridges in the first presentation pointed out about how you present information granularly. And then you can go down to the route. Now I'm going to pick what would seem like an arbitrary route. Birmingham off to Banbury. Why? Well, I live on this line, so I'm always interested to understand how the maintenance of the network changes. And what we've got is a list of all the problem structures on here, which may therefore necessitate some investigation or some monitoring of some way, shape or form. How do we get from thousands of structures to other structures? And then at specific type structures, we go into we can look at what runs there and what the clearance is associated to. Now, this is not just vehicles which currently run. This is also vehicles which may we want to run in the future, or we may be due to stop in the past. So forgive me while I jump back into my presentation. And so therefore another side of this is we talked about where we have to, once we got the trigger for information, how do we design and refine that? Again, the collation of all this data, super difficult to use. Understanding what the current rolling stock and the future rolling stock and the planned upgrades to the network is not something which is easily available. So knowing that we know now what the status quo is, how can we use that information to inform designs, meaning that engineers have less time to process and more time to inform? So again, I'm just going to very quickly jump into what that looks like. And using the same example, we have Hayford Station. So we're now in the process of we've got something we want to understand more. And in doing so, what does this station look like specifically? We're looking at where we've got problems, what duration of the platform have we got, where specifically on the vehicle is the issue, and we can navigate through to help the engineer understand more. More than that, we've also got things about history. What has changed? So we've got multiple different surveys. It allows us to predict trends. So in later survey gauging, survey steps, we have improved clearance. What's changed? Why has it changed? All these are critical informations to inform our assets. And finally, how do we very quickly look at the impact of making various changes? What happens if we put on a lift? Now, I'm not a track engineer, so I'm not going to go into the realms of what level of lift is plausible, but what is the feasibility of, if we could lift it, what impact does that have on clearance? So what we are trying to strive as a company and as an organization is how we use these multiple sets of data very efficiently to be able to put that in the hands of the engineers responsible for solving the problem. And so my final thought, as I know that we're tight on time, so apologies if this has gone slightly over, David, but my final thought on here is that better data is driving better gauging information. And better gauging information leads to better maintenance and design solutions. And really, we're about taking a huge volume of data, which the industry is collating, processing it into gauging information, and then putting that in the hands of maintenance engineers and design engineers. And we're delighted that these two projects, which we have worked in partnership with some of the great engineers in Network Rail and the supply chain, have helped us to come up with solutions which can exploit this gauging data better. So that's my very short and sweet presentation on how we have started to use some of this new data streams coming on board and to inform better gauging using software.
Thank you very much, Colin. And quite apart from the gauging application, a really good example of what Ian and others were saying at the beginning about how to provide information, how to turn, as you put, data into information and then into action. So really good practical example, as well as a specific example in terms of gauging. So we'll have questions just after 11:30. So if we can invite our final speaker to join us now. Dr. Colin Smith McGloin. Colin, good morning.
Good morning.
So Colin is product manager at Unipart Rail, covering condition-based maintenance and train and rail safety systems. Colin has extensive experience in implementing condition-based maintenance solutions for rail. And so we're going to be focusing with Colin on, as it says there, knowing your asset through in-service monitoring. So Colin, over to you. we'll give you your allotted 10 minutes, so we'll finish at 11:35. So okay. Over to you. Look forward to hearing from you.
Okay, thank you, David, and thanks for inviting me to present today. So in terms of what I'm going to cover, I'm going to give a brief overview of Unipart Rail. I'm then going to introduce the topic of in-service monitoring, and then look at one specific example around signalling assets and end on future innovation. So Unipart Rail, we're a £200 million business, and we operate in three core areas: signalling and traffic management, infrastructure, and traction and rolling stock. We're aiming to be carbon neutral by 2030. We're probably best known for our supply chain and logistics expertise, but as I'm going to show today, we're also kind of key in driving some innovations and new technologies in rail. We're part of the Unipart group, and this image is just kind of showing what the structure of that is. We exist as Unipart Rail. our Unipart Technologies group is key to kind of driving all of our digital and innovation solutions across the company. So not just rail, but in our other logistics and international business. The company I'm going to pick out from that list there is Instrumentel. Instrumentel were a spin out from Leeds University, who specialised in developing sensors for extreme environments. They kind of done their initial work in engine monitoring for Formula One, and they've now been able to apply that same sort of technology and techniques into the rail industry. They've developed a full monitoring solution for train assets, so covering things like engines, doors, and any kind of asset that you need to monitor on a train. They have the kind of full platform, and they're able to turn and manage that data into actionable insights that can be used to drive maintenance. So having sort of developed the equipment and technology necessary to monitor the train, we're now turning our attention to how can we use the train to monitor the infrastructure. The picture there on the right is just illustrating all of the things that you could potentially monitor from a train infrastructure wise. So you can pick up track geometry, you can look at the rail, S&C, the overhead line, third rail, track circuits, and you can also look at sort of collecting video and LiDAR data, giving you information about the infrastructure corridor. And I guess kind of try to answer, why would you want to do that? Well, it's a way of increasing the frequency of measurement of infrastructure, which in turn can lead to earlier warnings of potential failures. It helps you to manage operational issues because you've got data near live. So, you know, things like if you have a driver reported rough ride, you'd have the information available to determine whether it's track or vehicle. And also it supports the move that the industry is trying to make towards condition-based maintenance. The challenges that we have are, it's probably not yet technically feasible to replace all systems that we've got deployed on our dedicated infrastructure measurement fleet. And that can be due to cost, power requirements, size of the equipment, the need to maintain and calibrate that equipment, but also the kind of speed that the vehicle needs to go at to take certain types of measurements. How do those sort of benefits and challenges impact strategy? So on the left-hand side, we're aiming for preventative maintenance and being able to monitor asset on condition. And for that, we need more frequent data. On the right-hand side, there's an illustration there of a potential mobile infrastructure monitoring strategy where you still need the dedicated fleet, which can take kind of very high, accurate, compliant data on a scheduled basis, but overlapping that with more frequent data from in-service vehicles. And a example there of your P to F failure curve showing the F point there is where the asset fails. The P is the first time where you've got an indication that there's a potential for failure. If you're collecting data more frequently, you get a much earlier warning that there's something wrong with that asset, and you've got much better time to plan and intervene. So the two areas that we've been looking at, we're working with Network Rail on a design contest based around track geometry and vehicle dynamics, and the item I'm going to cover today is around monitoring the electromagnetic spectrum that railway signalling assets produce. So how does the sort of track circuit monitoring work? Well, the theory is any wire carrying a current produces a magnetic field, and we can put sensors onto a train to detect those fields. The track circuit itself, as a very basic high-level description, it uses the electrical signals to detect the presence of a train. It has a transmitter and a receiver, and if the receiver detects the signal, then that indicates that the track is not occupied. So you've got there an asset where it's carrying a current, that the rail is carrying a current, and that in turn will produce a field that we can monitor from a train. As an example of what we can do with that information, we fit sensors to the leading and trailing end of a train, and that allows us to kind of pick up, as in this example, for AC track circuits, the transition point between two blocks. So not only can we pick up the condition information, we can also determine exactly where that track circuit exists, and that can be quite useful in terms of being able to survey and understand exactly where those assets are located. Similarly, we can use the same sensors to monitor the condition of TPWS assets, the train protection warning system. We can pick up again their location and magnetic field strength. That data can then be combined to kind of give a high-level survey. So it can be important if you're looking to model the signalling system to understand exactly where all those assets are located on the infrastructure. And by using these sensors, it's a way of collecting that data automatically and then being able to verify the position and survey of those key assets, as well as being able to pick up condition and deterioration. In terms of where we're going next, we're opening a technology and innovation hub this year, and we're working with Ukraine to bring more academic and SME type research into the rail industry, similar to what we've done with Instrumentel. Yeah, and then questions.
Excellent, Colin. You gained some time back. Fantastic. They really appreciate that. We're going to go into the main Q&A now, if that's all right. So, but Colin, if I can just sort of open up a. Oh, hi, Colin. We lost you there for a second.
Just a Wi-Fi blip.
Yeah. So just before we go into the main Q&A, if I just sort of ask you the first question, if I may, Colin. So I mean, really interesting example of moving towards electromagnetic field monitoring. So where are you in terms of implementing that? I mean, because the potential there is enormous. Is that at trial stage, or has that now been rolled out?
So we've had a trial stage with Network Rail fitting that equipment to one of their recording units, and because Unipart actually manufacture TPWS AWS systems as part of their product line, and we can embed, effectively we're using those sensors and we can embed that technology into the actual product. Yeah. So yeah, it's quite an exciting, novel kind of use of physics and how you can apply that to rail. Excellent, really good.
So I'm going to, so first of all, if I could ask the audience to thank the two Collins, actually, because we didn't thank Colin Johnson. We thank the two Collins for their presentations. If I could invite the other speakers, and indeed anybody that wants to join in the discussion, to sort of turn their cameras on and join in. Just to say that if you we won't ask any questions. If you want to take a 5-minute break and go and make a cup of tea or whatever you want to do in your 5-minute break, but we're going to chat away till about 12 o'clock here. So we've got some good questions in the chat, which I'll open up. So the first one I'd like to ask the presenters about is, there's a general comment from Ian Maxwell, and I think that's probably the Ian Maxwell of the Office of Road and Rail. And Ian says that there are now many individuals in the rail industry who believe in data-driven maintenance, and certainly I'm probably pretty sure that everybody on the call today is a convert to that. But Ian says he thinks there are two blockers. The sheer quantity of assets that need to be fitted with sensors and the cost of doing so, point one. And secondly, the challenge of processing and reviewing the huge amount of data that comes from these sensors, and you only get benefit if you can use the information wisely. So I think we've seen examples that touch on both of those blockers, but I'm interested if if the speakers would like to sort of pick up, do you agree with Ian? And if so, what do you see as the solution? So his first one is the sheer quantity of data or assets rather that need to be fitted with sensors and the cost of doing this. So what are the thoughts on sensor profusion versus, because Ian, you touched on, you mentioned, the aero engines, which have thousands and thousands of sensors. Lewis and Gareth, by contrast, were talking about not censoring things because their work relies upon manual inspection from time to time. So just open it up to the floor. What are the observations? Ian, you're talking, but you're muted. You've muted yourself again. You've double muted. Click again. Every time you click it, Oh, we'll have to come back to you then, Ian.
I could probably answer the first point about the number of sensors. So, I mean, in-service monitoring is a way of managing that. So if you can pick up the information from about the infrastructure from a train, then you don't necessarily have to embed those sensors into every piece of line-side equipment. So that can be kind of one strategy. It's kind of important to think through the balance of whether you're fitting sensors to a train or, are you going to fit hundreds of sensors to line-side equipment?
That makes a lot of sense. If you can monitor from a train, then there's clearly less cost than monitoring the equipment. So that's a really good point. Ian, are you unmuted now? Did you want to?
Yes, we're unmuted now. Yeah. I think it's probably about priorities, and again, it probably comes back to what I was saying at the start: is what is the client really wanting out of this? I mean, where I'm working in Balfour Beatty, and where I used to work with Colin there, we're concentrating at the moment on looking at level crossings for the client, because the client ultimately wants to be able to get away from having to do cyclic maintenance on level crossings. So we're providing sensors and systems into those level crossings that will ultimately enable that to happen. So in that case, the priority was to fit level crossings. But Ian's absolutely right. I mean, there's a vast amount of components out there, and I suppose one could argue that it only takes one component to fail, and that's it, your railway stops working. But I think you've got to take this piece at a time in bite-sized chunks and decide what your priorities are, what you're trying to achieve, and ultimately fitting sensors into new equipment when it's built, so that if we've got a standard that we can create, then all those sensors work together all into whatever systems we've got, then that's a big step forward as well.
Okay. I can see Lewis wants to come in, but just before I bring you in, can I just say to the audience, if you want to ask a question, just put your hand up, your virtual hand, using the toolbar, and I'll invite you to come in. Lewis, you wanted to come in at that point.
Yeah, just a very short comment. I agree with that, but I think sometimes we're comparing airplanes with railways, and we forget that the railways were built over 180 years, and some of them we don't even, a plane is a beautiful thing where you know exactly where each piece of equipment came from. All of them were designed very carefully. They're all assembled in the same way, and in many senses, all these engines are exactly the same thing, repeated 100 times. We are dealing with crossings that some of them are 100 years old, equipment that we don't really know when it was built, how. Some of them were not designed. And so in some senses, I think it's much more challenging for us to gather this data, and they are much more customized and one-of-a-kind structures and elements across the board. So the reason why we're not at the same level as other industries is not because we are behind, it's because our problems are much, much more complex than they are. That's
Sorry, Luis, I think I've accidentally muted you.
I'm sorry. Let me just get the last phrase. I think the pathway to that is to start with components and elements which are more repetitive, like track, for example, where we can get more stuff. And the stuff I'm more worried about, which are things like masonry bridges, I'm afraid are going to be at the very end of the queue, because those are really, really nasty.
Thank you. I'm going to come back to you in a minute with a question about modelling assets. But John, you do you want to come in? You've got your hand up, and really interested in the parallels that you drew in your presentation. But go ahead.
Yeah, and I think it's interesting to hear the challenges that rail faces, because it is quite similar to defence. And in our world, Louise, you talk about bespoke, one-off pieces of kit. Okay, as we might build a few of them, but everyone is different because every single platform is different subtly when they're built because of what they are. So it's exactly the same challenge. So I guess from our perspective, we've had a lot of manual and traditional data for many years, which we've collected, and we use that to inform a risk assessment approach where we look at actually what's the right areas to monitor and measure. And as we go forward now in our new systems, we fit sensing technologies for the future stuff based on what we've learned from history. And I think if you're trying to roll out across a large network with many challenges, there's got to be existing data already that enables us to make decisions around which bits we should monitor, which is what Ian was saying about crossings and things. I think it's selectively picking. And I guess for me, it's probably understanding the KPIs ultimately the business. And if that's on time, trains and safety, it's picking the areas that have criticality in that and then working backwards. Because the challenge, as Ian's highlighted in the chat, is you could measure anything and everything. You can measure on an engine, you can measure coolant, you can measure flows, temperatures, pressures, but actually something like vibration is probably the one that tells you you've got an issue you need to worry about. And it's about picking those kind of areas. And that's the strategy we take in our world to avoid fitting a plethora of sensors that then is data, extrapolation at huge levels to monitor.
And I thought the other thing that must be applicable in the defence sector, certainly with submarines, as you say, you're not able to pick up the data, and I guess you have to provide tools and instructions and training for the onboard technicians. You've got to make them completely self-contained, I guess. In a way that you perhaps don't have to do in some other sectors.
Yeah, that's a fair point, David. There's reams of documentation to support everything that we supply, and I suppose also regular training. So we put regular training on for operators so they can understand the key safety issues, and repeat training and refresher. And we're looking at kind of digitized versions of training now, so that actually we can get away from a little bit of kind of face-to-face time, which is more difficult, especially with COVID, but also just generally, I think it means you've got that refresher point so that you can kind of take people through it. Because we've certainly found in history there is a big correlation between the amount of training and asset failure in terms of, people do disconnect and reconnect the wrong things. It happens, and it is about kind of reinforcing that message. That's
really good. Oh, there's some questions coming through from the audience, which is great. If you want to ask them verbally, then put your hand up. But otherwise, I'll read them out for you. So just a reminder, if you want, please, you've got a great panel of experts here. So if you've got some questions, just put them in the chat or put your hand up, and I'll bring you into the conversation. So Colin, you wanted to. I'll come back to the audience question in a minute. I think you wanted to make an observation. You've got your hand up.
Well, I think, yeah, absolutely. It's one maybe from a more kind of from our business perspective, and the question raised by Ian Maxwell. I think that one of the key points we see is actually it's about the processing, reviewing the second part of that challenge. We collect in the industry a huge amount of data, and I think this may be a function of the disconnected railway in some respect, that people are collecting some data for one purpose, but others can use that data for other purposes really effectively. And too often I've heard that we need to go out and collect that data, when actually what we need to do is signpost it to someone who's collecting something which could serve that purpose, and the investment to be made in post-processing, which is in my experience significantly cheaper than collecting data. So I think that honestly, the challenge in the railway is more weighted towards how we use the data which we currently collect wisely. And then once we know how we use it, then it may be down to to collecting more of it or different revenue streams. But you only have to look at companies like Perpetua and what they do with vibration analytics and all those kind of things, where one sensor can serve so many purposes, and that's one of those kind of examples. And the railway is not alone. Automotive sectors, they will use a lot less sensors but do a lot more with them to serve various different systems. So yeah, I think the challenge is very much in the second part.
So there's some great advice there, and it goes back to what I think Ian and others have said about Ian Bridges, that is, ask the customer what they want. I guess it goes to Luis and Gareth, understand the failure mechanisms. You're saying, Colin, use the data we've already got before we go out and collect more. I think there's some great advice in there. I'm going to turn to an audience question now. I've got a really interesting question from Ant Monaghan, who's, this is an interesting angle. He's saying, how does the panel think that the announced rail data marketplace is going to change data collection and use in this context? So I'm just wondering if you all spotted the announcement. The government announced the Rail Data Council putting £5 million into making available rail industry data. What I'm not clear about is the extent to which it's asset data, which we've been tending to talk about today, as against customer data, or whether it's both. But I'm just interested in I think maybe if we take it from the generic concept of a place you can go to access rail data. What do you think of that? Colin, you've got your hand up. Was it to come in on that? Colin Johnson, that is. Did you come in on that point?
I think it's a really interesting concept. I think the key point is there's a lot of people in our industry which their commercial model to collect data and just provide. So the real challenge. I think there's one to be great for a portal to say what data is availability, but I think the commercial element behind it is one which is going to be a real tough challenge for the industry to cope with. I think that in the past that a lot of people, there's a comment I think from Ant, which is, I'm yet to find a data set in the industry which has been really useful. Agree with that sentiment. All data can be really useful. The question is if you have to pay for that up front to see if it's useful, that could change the dynamic of how we learn and all those things. So I'm interested to understand what data actually appears in that. And I think that some people may be surprised about the cost of how much it is to collect data as well. And that might be shown in that model, that data might seem very expensive, but data is expensive to collect. So that's just an underlying concern and opportunity, I think. But just say, let's see how it goes.
There must also, I guess, be a question about how reliable is the data, how current is it, what's the quality attributes attached to it, and so forth. Because wrong data that purports to be data is just going to mislead you.
Yeah, it's volatile. It is
it's
volatile.
Your volatility point. Would anybody else like to pick up on that, or I'll move on to the next question, which is from Matt Brough, which has got a like against it. It says, with huge volume of data available for each asset, there are a myriad of opportunities to use this to manage specific assets better. However, how can this data be considered across multiple asset types to make network system decisions rather than asset subsystem specific decisions? And I think as an undercurrent of that is we see lots of what you might unkindly call point solutions to monitoring something, which then, they either the data isn't widely available or the potential benefit of a system level thought isn't there. John Constable, do you want to come in on that?
Yeah, David, it's probably worth picking up. So part of the work we've done in the defence sector has been applying autonomous navigation, actually, but part of our engine that drives that is an optimization tool. So effectively, we're using AI and machine learning techniques to understand complex data, so much different types and variability of data. And I think to answer the point that's asked, it's sucking all of that in, but then being able to process that quickly and sensibly and be able to make system level decisions. And I tried to kind of drop a little hint at the end of my talk today that, if you imagine you've got a fleet of trains operating, mixed fuels, mixed fleets, different journeys, different locations, different assets on board, different track conditions, different people, different cost signatures, penalty clauses, all those kind of things. There's a huge amount of stuff there that kind of really feeds into it. But if you can manage that at a system level, and we can use emerging digital technologies to help make decisions, then that to me is got to be where the future goes, because actually you start to look at things like machine learning, where you can look through concessions and other things of the past, and you can make predictive decisions for the future. And I think that's the real strength at a system level, is let's use those technologies to help make the decisions from the plethora for the data lakes. And I think that's one of the big challenges been highlighted in the chat already, was the amount of data that's being generated across industries, that most of it's kind of low level, but at a system level, there's probably only a handful of key points you really want to understand.
And does that point to a through life management or through life relationship, as you experience in defence, rather than what sometimes happened in the past, where a client goes out and buys something to monitor something and then just that's the end of the relationship? Because I think what you're highlighting is constantly learning, and as Luis and Gareth illustrated with their presentation, you illustrated that around you took bridges and structures as an asset, but you are using available data and developing new tools, so you're learning and constantly developing. The question I wanted to ask Luis and Gareth is, presumably that exact same approach both is applicable across other asset types with different data, but also applicable across different assets to as per the question. What are your thoughts on that?
I think that's one of the huge challenges we face. And I think one of the issues we face is that we are making decisions on asset-specific decisions. So we are allocating budgets for bridges, and then within that budget you make decisions, and then you're allocating almost an independent budget for track, and you're making decisions on track based on an available budget that does actually not compare the needs across assets. The problem there is that the performance indicators we have are actually not comparable in many senses. So how do you compare the duration of a bridge versus the duration of track versus the duration of signaling? And I think the only way we can do this is look at risks, look at the consequences of all of these things. And we would definitely like to get on board onto that principle, because that would allow us to compare monitoring of a bridge with monitoring of trains to analyze the performance of track and compare them side by side and say, if I put my money here, this is what I get out of it. If I put it there, this is what I get out of it. And I could compare those in a transparent way that I would not be afraid to go to the stakeholders and says, this is why we spent the money, rather than we assign 30% there and 30% there because that's what we've always done, and then each of them sorted it the best way they could. So I'm not trying to sound very negative, but I think as we move to more data-informed systems, we will be able to do this because we have evidence and because we have expertise that starts to span across different assets, where traditionally this was a personal experience that was not actually founded on any solid data. So as we move towards the data lakes and everyone is using the same data to do different things, it becomes much easier to compare things across assets. Hopefully we'll get there, but it's still a long road.
No, that's good. Ian Bridges, you've got your hand up. Good advice there, Luce. And that's an interesting challenge in an industry where we still tend to think by assets. We still tend to be bridge engineers or PUA engineers or signal engineers, and we manage in that way. So that would be an interesting conversation amongst my former colleagues in those fraternities. Ian, do you want to come in?
Yeah, I was just going to add, actually, it's quite interesting. We mentioned spot monitoring there, which I think I quite agree doesn't necessarily achieve a great deal. But there's quite a well-defined list of items that you monitor in interlockings when you're working there. So if we're going to monitor a level crossing now, we monitor a lot more than just the actual operation of the level crossing. We monitor track circuits, we monitor all sorts of other things, we monitor signal aspects. Now that's where it does start to get interesting, because that data then can be used for other things. Because if you know when the signal is at red, you know where the trains are, you can start to say, well, how many trains are approaching red signals? Now that's not necessarily a good thing. So we can monitor that. We can monitor exactly where a train is in real time. We can monitor how fast the train is going because we know the length of a track circuit, so we can measure how fast it's going. There's all sorts of other stuff can come out of that as well. And this was why I made my point about sometimes you need just that little bit more data to make a lot more sense of what you've already got. And I think that's probably a good example of that thing.
Yeah, excellent. So there's a bit of good advice in the chat here from Pete Johnson, picking up the point solution problem, and he's pointing out the cross-industry remote conditions monitoring group at RSSB have done some work on that, and he gives the references there, looking at a layered approach. So I'd recommend to those on the call to pick that up. There's a question here about data collection from Tony Laird of Amy, and he's asking whether there's an opportunity within the rail industry for the development of technology for data capture, such as satellite and drones. Other industries such as utilities and highways are using these things. Anybody want to pick that up? What are the thoughts on that?
There definitely are some capabilities for incorporating drone inspection. So I think Luis and I have done a case study where we've looked at incorporating drone inspections for bridges to then feed into our more strategic level models. So it depends. It goes back to Ian's point. It depends on what question you want to ask, or what the priority is of the stakeholder. But there's definitely means to incorporate drone and satellite imaging into strategic and tactical models.
Okay. Go on, Colin. Go ahead.
Are used in railway monitoring, and I think in terms of satellite data, I think there's a presentation. Is it tomorrow or maybe this afternoon on SatSense are doing one on what they've done? So stick around for that to see.
I was going to say there's also a question in the chat about digital twins, using digital twins for modelling, and I think I'm right in saying, I'm looking for it now, but I think we've probably got a presentation on that. But if not, we certainly acknowledge that that's and we've we've done a number of presentations in RIA events around that, and there's clearly an opportunity to use digital twins to model asset behavior, and it, in a sense, what Gareth and Louise are doing can be described almost as it's a decision support tool, if you like, but it's also effectively a digital twin. So I'll just see if we've got any last questions, as we're almost on the hour, so I should probably draw it to a close at that point. But just to once again thank our excellent speakers. But before I call for a round of applause, if I could just remind you, everybody, that if we've been talking about knowing our asset this morning, this afternoon at 3 o'clock, we're going to be looking at collecting data, methodologies around collecting data. Tomorrow at 10 o'clock, we're going to be interpreting data, and tomorrow at 3 o'clock, we're going to be looking at what the impact of that is on how you change your business. So although we've touched on a lot of those subjects today, we'll go into those in more depth over the next sessions over the next day and a half. So thank you to the audience for joining us and participating and giving us lots of questions. Hopefully in the not too distant future, we'll be doing physical unlocking innovation events and inviting you to actually be a real live audience. But thank you for being a great audience today. And can I ask you to be a great audience and thank our speakers for their excellent presentations in the customary time-honoured Teams manner. So thank you everybody, and enjoy the rest of your day. And I hope you'll all be back at 3 o'clock for the next part of the Unlocking Innovation data-driven event.